What if I told you that the Inca Empire moved millions of gallons of water across some of the most treacherous mountain terrain on Earth without a single pump, motor, or modern tool? Deep in the Andes Mountains, carved into sheer cliff faces and snaking through impossible gorges, lies a network of channels that defies everything we think we know about ancient engineering. These waterways climb to elevations above 14,000 feet, that's over 4,200 meters, where the air is so thin that modern construction crews struggle just to breathe. Yet somehow, the Inca made water flow exactly where they needed it. Experts have analyzed these systems for decades, and what they've discovered challenges our assumptions about what's possible without modern technology. How did a civilization without the wheel, without iron tools, and without written mathematical formulas create hydraulic systems so sophisticated that many still function perfectly today, 5 centuries after their construction? Hanan, you're standing in the sacred valley of Peru, surrounded by peaks that pierce the clouds at heights that would dwarf most buildings you've ever seen. The landscape is vertical, hostile, unforgiving. Rivers thunder thousands of feet below in narrow canyons, while above you, glaciers cling to mountains that seem to touch the sky itself. This is where the Inca chose to build their empire, and this is where they needed water. Not just in the valleys where rivers already flowed, but high on mountainsides where they carved agricultural terraces into slopes so steep you'd need climbing gear to reach them today. When Spanish conquistadors first witnessed these water systems in the 1530s, they were stunned. Pedro Chiesa de Leon, chronicler of the conquest, wrote that the Inca channels seemed to defy the very laws of nature, carrying water to places where no water should flow. Modern engineers who study these systems report something equally remarkable. The channels maintain precise gradients, sometimes for distances exceeding 20 miles, that's over 32 kilometers, without varying more than a few degrees. Dr. Kenneth Wright, a hydraulic engineer who has spent over 3 decades analyzing Inca waterworks, states that the precision required to achieve this consistency over such distances would challenge even modern surveying equipment. These weren't simple ditches, they were calculated, engineered systems that demonstrate a profound understanding of fluid dynamics, gravity, and physics. But how exactly did they accomplish this feat? To understand the genius of Inca water engineering, we need to start at the source. The Inca didn't fight against geography, they worked with it, turning the mountains themselves into a massive hydraulic machine. Look at how they captured water at the highest possible elevations. Unlike modern systems that pump water uphill at tremendous energy cost, the Inca began their networks at natural springs, glacial melt streams, and high-altitude watersheds, sometimes above 15,000 feet or 4,500 meters. By starting at these heights, they harnessed gravity as their engine. Every drop of water they captured would naturally want to flow downward, and the Inca simply directed that desire. Archaeological surveys conducted by Dr. Alfredo Valencia Zegara at sites like Tipón, near Cusco, reveal intake structures carved directly into living rock at the sources of mountain springs. These weren't crude holes in the ground, they were engineered collection basins with settling pools where sediment could drop out before entering the main channels. The Inca understood that sand and debris would wear away their channels over time, so they built filtration into the system from the very beginning. What's extraordinary about these intake points is their sheer number. At major sites, researchers have identified dozens of separate springs being tapped simultaneously, each feeding into a network that would eventually converge and distribute water across miles of territory. Now follow the water as it begins its journey. The Inca carved channels directly into solid bedrock, creating pathways that have survived half a millennium of earthquakes, landslides, and weathering that would have destroyed lesser construction. If we examine closely the channels at Machu Picchu, analyzed extensively by Wright and his team, we see something remarkable in their design. The channels maintain an average gradient of between 1 and 3%. That means for every 100 feet of horizontal distance, the channel drops between 1 and 3 feet. This isn't arbitrary, it's the perfect balance. Too steep, and water accelerates to destructive speeds that would tear the channel apart. Too shallow and water stagnates, sediment accumulates, and the system clogs. The Inca hit the exact middle ground, and they maintained it for distances that boggle the mind. At Cumbaymayo in northern Peru, a stone channel carved around 1000 BCE by pre-Inca cultures but later incorporated into Inca networks, runs for over 5 miles, that's 8 kilometers, while maintaining this precise gradient. Modern engineers attempting to replicate this feat with laser transits and GPS find it challenging. The Inca did it with string, stakes, and an understanding of water that bordered on intimate in. But here's where it gets strange. Water flowing downhill in a mountain environment faces a problem that seems insurmountable. The terrain doesn't cooperate. Mountains don't descend in gentle, uniform slopes. They're fractured by gorges, interrupted by cliff faces, and broken by valleys that cut across your intended path. So how did the Inca keep water moving when the ground beneath their channels disappeared? Look at the solutions they engineered. Where cliff faces blocked the way, they built canals that cling to vertical rock walls like something from an architectural fever dream. At Ollantaytambo, channels carved into sheer granite faces run hundreds of feet above the valley floor, following contour lines so precisely that the water never gains dangerous speed. Where valleys or quebradas cut across the path, they built aqueducts. Not the soaring Roman stone arch aqueducts you might imagine, but lower profile structures, often consisting of stone walls filled with rubble and faced with precisely fitted stones, creating artificial hillsides that bridged the gaps. These structures, some reaching heights of 30 feet or 9 meters, were designed to handle not just the weight of water, but the seismic activity that regularly shakes the Andes. Dr. Jean-Pierre Protzen of the University of California, who has studied Inca stonework for decades, notes that the joints between stones in these structures are so tight that you cannot insert a knife blade between them, yet they're not mortared. The precision of the fit alone holds them together, and that precision allows the stones to shift microscopically during earthquakes without the structure failing. What's even more puzzling is how they controlled the water's energy. Imagine you're an Inca engineer watching water flow down from a spring at 14,000 feet to a city at 11,000 feet. That's a vertical drop of 3,000 feet, nearly 915 meters. If water fell freely down that distance, it would hit the bottom with enough force to destroy anything in its path. The Inca solved this through a technique that modern hydraulic engineers call energy dissipation. But the Inca version was built from stone and genius. They created drops, small waterfalls within their channels, where water would fall a few feet, then hit a basin, then fall again. These weren't accidents of terrain. They were engineered features carved deliberately into the channel every time the natural slope became too steep. At Tipón, you can count over a dozen of these drop structures in a single channel system, each one bleeding off just enough energy to keep the water manageable. Between the drops, they used another technique. They narrowed and widened the channels. When water enters a narrow section, it speeds up. When it emerges into a wider basin, it slows down and deposits sediment. This wasn't just erosion control, it was hydraulic computer programming written in stone. Nevertheless, the challenges didn't end with controlling speed. The Inca needed to distribute water, not just move it. A single channel descending from a mountain spring was useless if it only served one location. They needed networks that could branch, divide, and deliver water to dozens or hundreds of destinations. Look at the distribution systems at Machu Picchu. From a single primary channel fed by springs on the mountain above, the Inca created 16 fountains descending through the city in a cascading sequence. Each fountain is carved from a single block of stone, with a precisely shaped spout that creates an aesthetically pleasing water arc. But these aren't just decorative, they're functional distribution points. After water serves the upper fountains for drinking and ritual use, it's channeled to agricultural terraces below for irrigation, then ultimately to drainage systems that prevent the steep mountainside from becoming waterlogged and sliding away. The entire city is an integrated hydraulic system where water serves multiple purposes as it descends. Dr. Ruth Wright, working alongside Kenneth Wright at Machu Picchu, documented how the site's primary water source, a spring called the Machu Picchu Spring, delivers approximately 80 gallons per minute. That's about 300 liters. But through careful distribution, this single source supported a population estimated between 300 and 1,000 people, plus extensive agricultural terraces. Moreover, The Inca understood that water systems require constant maintenance. Modern engineers often forget this. We build systems and expect them to run untended. The Inca knew better. They organized their empire around the concept of mita, a labor tax where every able-bodied citizen owed work to the state. A portion of this labor was dedicated to maintaining the water systems. Channels had to be cleared of debris after storms. Stone linings had to be repaired when they cracked. Intake structures had to be cleaned when sediment built up. This wasn't occasional maintenance, it was constant vigilance. Spanish colonial records document that entire villages had the responsibility of maintaining specific sections of major canals, passing this duty from generation to generation. Without this organized empire-wide maintenance program, the systems would have failed within years. But with it, many functioned continuously for over 400 years, and some still flow today. This reveals something crucial about Inca engineering philosophy. They didn't try to build systems that wouldn't need maintenance. They built systems that could be maintained with available tools and organized labor. It's a fundamentally different approach than modern engineering, which often prioritizes minimizing maintenance, and in the Inca context, it was arguably more sustainable. Interestingly, the Inca also demonstrated sophisticated understanding of water's behavior in ways that seem almost impossible without modern fluid dynamics theory. At several sites, archaeologists have found structures that function as siphons. A siphon is a way to move water across a depression, down one side and up the other, using atmospheric pressure and gravity. The Romans built inverted siphons using lead pipes, but the Inca had no such pipes. Instead, at sites like Rakchi, researchers have documented channels that descend into valleys and rise on the other side using carefully shaped stone conduits. The engineering required to make this work without pressurized pipes is extraordinary. The channel must be completely sealed and follow a precise profile to prevent airlocks that would stop the flow. That the Inca achieved this with stone construction speaks to a level of hydraulic understanding that conventional history rarely credits to pre-Columbian civilizations. Dr. Charles Ortloff, who has published extensively on ancient water engineering in journals like the Journal of Archaeological Science, notes that computational fluid dynamics models of Inca channels reveal design features that optimize flow and minimize turbulence in ways that suggest either extensive empirical testing or theoretical understanding that we haven't fully acknowledged. Furthermore, the Inca adapted their water systems to local environments with remarkable flexibility. In the arid coastal regions, they built filtration galleries, underground channels that collected water seeping through alluvial deposits, protecting it from evaporation in the desert heat. In the high Puna grasslands, they created extensive systems of cochas, artificial ponds that captured seasonal rainfall and released it slowly for irrigation during dry months. In the steep eastern cloud forests, they built drainage systems as sophisticated as their irrigation systems, removing excess water before it could trigger landslides on the saturated slopes. Each environment demanded different solutions, and the Inca provided them. This wasn't one-size-fits-all engineering. It was adaptive, responsive design that considered local hydrology, geology, climate, and agricultural needs. The scale of this adaptation becomes clear when you consider the extent of the Inca Empire. At its height, around 1530 CE, it stretched over 2,500 miles, that's 4,000 kilometers, from modern-day Colombia to Chile, encompassing coastal deserts, highland plateaus, and Amazonian cloud forests. Managing water across this diverse geography required not just engineering skill, but organizational capacity that rivals any modern bureaucracy. So, what theories explain how the Inca achieved this hydraulic mastery? The mainstream archaeological position, supported by researchers like Kenneth and Ruth Wright, holds that the Inca developed their water engineering through centuries of accumulated knowledge, careful observation of natural water flow, and extensive empirical testing. They argue that the Inca had skilled engineers, possibly trained in schools we haven't yet identified, who understood gradients, flow rates, and erosion through practical experience, rather than written formulas. Evidence supporting this includes the existence of test channels at some sites, places where multiple channel designs were tried in parallel, suggesting experimentation. The presence of standardized measurements in Inca construction, like the approximately 12-inch or 30-centimeter module that appears repeatedly in their buildings and channels, indicates systematic design approaches. Some researchers propose that the Inca possessed mathematical and engineering knowledge more sophisticated than previously believed, possibly recorded in quipus, the knotted cord recording devices that Spanish chroniclers describe, but which we still can't fully decode. Dr. Gary Urton of Harvard University, who has studied quipus extensively, suggests they may have recorded not just census data and inventories, but also technical information, possibly including the specifications for water systems. If true, this would mean much of the Inca engineering knowledge was destroyed when the Spanish burned quipus as pagan objects. Alternative theories suggest the Inca inherited and expanded systems built by earlier Andean cultures like the Tiwanaku, Wari, or Chavin, which demonstrated advanced hydraulic engineering centuries before the Inca rose to power. This theory has merit, as sites like Cumbaymayo predate the Inca by over 1,000 years, proving that sophisticated water engineering was a long-standing Andean tradition. Yet mysteries remain. We don't know how the Inca calculated the gradients for their channels over multi-mile distances without surveying equipment. We don't fully understand their quality control methods, how they ensured construction crews in different valleys were all building to the same specifications. We don't know the identity of their master engineers, as no Inca engineer's name has survived in the historical record. Ongoing research continues to reveal new aspects of these systems. Ground-penetrating radar surveys are discovering buried channels we never knew existed. Hydrological modeling is revealing the true sophistication of their distribution networks. And archaeologists working with descendants of the Inca, who maintain traditional water management practices in some Andean communities, are learning that oral traditions preserve engineering knowledge that hasn't been written down. What we're discovering is that Inca water engineering wasn't primitive or lucky. It was the result of deep understanding, careful planning, and massive organizational capacity. The significance of these ancient waterways extends far beyond historical curiosity. In a world facing water scarcity and climate change, the Inca systems offer lessons we desperately need. They demonstrate that sophisticated water management doesn't require energy-intensive pumps and treatment plants. It requires understanding your watershed, working with gravity instead of against it, and committing to long-term maintenance. Communities in Peru and Bolivia are reviving abandoned Inca channels to irrigate terraces that have been dry for centuries, finding that these ancient systems still work and still produce abundant crops without modern inputs. The Inca proved that you can support large populations in difficult terrain sustainably if you engineer with intelligence and maintain with dedication. Their water systems stand as monuments to human ingenuity, sophisticated understanding of physics and hydrology, and the power of organized civilizations to accomplish what seems impossible. 500 years after their empire fell, their water still flows through stone channels they carved with bronze chisels and stone hammers, a testament to engineering that transcends the technology available and reaches the timeless principles that govern how water moves. So what do you think made the Inca such masters of water engineering? Was it centuries of accumulated knowledge passed down through generations, or did they possess theoretical understanding that we've underestimated? Share your perspective in the comments, and if you've visited any of these ancient water systems in Peru or Bolivia, tell us what struck you most about seeing them in person. If you want to explore more examples of ancient engineering that challenges our assumptions about what was possible before modern technology, check out our other